All right, welcome everyone. So pretty exciting today. Today we're going to be talking about geometric series. And this is really one of our really important special types of series that we're going to be talking about quite a lot. And we're going to introduce them here. So today we're going to see what are we going to see? Well, we'll see the actual definition. That'll be helpful. We're actually going to be able to determine when these types of series are convergent, when they're divergent. And actually, what makes these so nice is we actually have a nice formula for the sum. Very rare that this happens, but for geometric series, we actually have a nice formula for the sum when the series is convergent. All right, so let's get into it here. So let's start with the definition. What is a geometric series? And we kind of talked a little bit about this when we first started talking about sequences. And so we actually talked about geometric sequences. So let's just recall what those were. And we had the special formula, a times r to the n. And if we wrote out the first few terms of that sequence, first term is a, second term is a times r squared, and so on. And essentially what's happening as we go from term to term in this sequence, we're really multiplying by a factor of r. So we're multiplying by r. To go from the first term to the second term, we multiply by an r. To go from the second term to the third term, what do? We multiply by an r. And so each consecutive term, we're just multiplying by additional factor of r. And so a lot of times we call this r value the ratio, or the common ratio. So this r value is going to be important. And we have this geometric sequence. So to form a geometric series, what do? Well, essentially, we just try to add up all the values, all these terms in our geometric sequence. So that's what you can see here in the definition. What is a geometric series? Well, it's a plus a times r plus a times r squared plus a times r cubed, and so on. Just keeps going. We're trying to essentially add up all the terms in our geometric sequence here. And writing that in sigma notation, we can write this as a times r to the n, where we're doing the sum from n equals 0 to infinity. Now here, we're using the starting index as n equals 0. So there is a kind of an alternative version of this where you can write this, and sometimes it's helpful, where we start our general starting index at n equals 1. And the only adjustment there is then it's a times r to the n minus 1. So this is just another form, another representation of this exact same series. Sometimes it's helpful to start with n equals 1. But for the most part, in the examples we're going to be looking at, we're going to be starting at n equals 0. But n equals 1 is also fine. So if you were to write out the first few terms of this, you would see you'd get exactly the same thing. All right, so let's talk about the partial sums here. And we're going to work on the partial sum when r does not equal 1. So we know for convergence of a series, how does a series converge? Well, the sequence of partial sums has to converge. All right, so let's start out. And let's just think about what maybe the first two terms of our sequence of partial sums. What would S1 be? Well, that's just where we take the first term of our sequence, and that's it. So it would just be a. What would S2 be? Well, it would be a plus a times r. So we take the first two terms, add them together. What would S3 be? It would be a plus a times r plus a times r squared. And so in general, if we kept doing this, Sn would be a plus a times r plus a times r squared. Maybe we'll write out another one there. And then we keep going. And then we would get up to a times r to the n minus 1. So essentially, we're adding up the first n terms here of our sequence to get this S sub n. All right, so this would be our S sub n. But this is written out. There's some ambiguity here with these dots. So we say the pattern keeps going. But you can see here this formula for S sub n. This is a nice formula. Everything is clearly defined. How we're going to get this is we're going to take this equation and we're just going to multiply both sides by r. So let's multiply the left side by r. We get r times S sub n. And let's multiply everything on the right side by r. So what are we going to get? Well, we'll get a times r plus a times r squared plus a times r cubed plus a times r to the fourth, and so on. And then instead of having a times r to the n minus 1, at the end, we're going to have a times r to the n. And what we do is we have these two nice equations here. And if you're looking at them, you see a lot of overlap. So there's a lot of similarities between this equation and this equation. And what we're going to do is we're going to subtract. So essentially, we're going to kind of subtract this equation, or we're going to subtract this equation from our previous one. And so what do we get on the left side if we do that? Well, we get S sub n minus r times S sub n. And what do we get on the right? Well, let's look. And this one's kind of fun, because you get so much canceling. So remember, we're subtracting here. So we're subtracting everything in this line from the line above. And what we notice is that we have an a times r and an a times r here, and we're subtracting, so those cancel. Then we have an ar squared, and we have an ar squared here. We're subtracting, so those cancel. And we keep doing this. The ar cubes would cancel. There would be an ar fourth up here. That would cancel. And then eventually, since we're getting to a times r to the n, eventually before here, there would have been an a times r to the n minus 1. So that would have canceled. And so everything gets canceled off except the very first term here and the very last term here. But everything else is canceled off. So what we're left with is a minus a times r to the n. And we want to solve for S sub n here. So now we can factor both sides and solve. So if we factor, we get S sub n times 1 minus r on the left and a times 1 minus r to the n on the right. And we can divide by 1 minus r just so long as r does not equal 1. So here we make the assumption r does not equal 1. And that's so we can divide by 1 minus r. Otherwise, we'd be dividing by 0, and that's no good. So we make that assumption, and this gives us our nice formula here. Divide both sides by 1 minus r. We get our nice formula. So I'll leave it for you, but try and work out the general form for our partial sum when r does equal 1. But essentially what we're doing there is we're adding up. If you look at our sequence of partial sums here, these r values are all just going to be 1. So S3, what would S3 look like? It would just be a plus a plus a. So we'd be adding up 3 copies of a. What would S2 look like? It would be a plus a. So we're adding up 2 copies of a. So essentially S sub n is just we're adding up n copies of a, or it's the same thing as n times a. So maybe try to convince yourself of this, but try for yourself. All right, so we have these two nice partial sums. Well, we can actually then use these to show that our series is convergent or divergent, depending on what the R value is. And so, again, geometric series is one of the very few series where we know what's going on, and we actually know the sum. So most of the action is happening with this R value. So we know the series converges as long as the absolute value of R is less than 1. If the absolute value of R is greater than or equal to 1, the series diverges. And if we know it converges, so if the absolute value of R is less than 1, well, then we can actually show that the sum is this value A divided by 1 minus R. So this is the actual sum here. And like we said, we know it converges as long as the absolute value of R is greater or less than 1. Another way to think of this is the R value is between -1 and +1, but not equal to. So R is greater than -1, but less than +1. Otherwise, it diverges. All right, so we're going to actually show a couple cases for this, maybe one case, we'll see. But there's a few different cases to actually prove this result. There's a few cases we need to look at. So there's the case when R is less than or equal to -1, and we know it diverges in this case. It converges in this case, diverges here when R is equal to 1, and it diverges when R is greater than 1. So for most of these R values, it diverges. But when we have this nice inequality here, when R is greater than -1 but less than +1, our series converges. So we'll prove it for this case. We'll prove this result for this case. And it comes down to how do we show that a series converges directly? Well, if we have our sequence of partial sums, we look at the limit of the sequence of partial sums. So calculating the limit of S sub n as n goes to infinity, if this limit is a number, well, then our series converges. If this limit is infinite or does not exist, then it diverges. So we're going to show this for the case right here, where R is between -1 and +1, but the other cases are going to be similar. So let's fill in, what did we know our sequence of partial sums is? We just found a nice formula for that. We found it was A times 1 minus R to the n over 1 minus R. And when we look at this, the A value is a constant, the R values are constant, so the only thing with an n here is this R to the n. And we've actually investigated the behavior of such an expression before. So it's going to be helpful to remember that the limit of R to the n as n goes to infinity, there's a few different cases here. And we investigated all of these when we talked about the limit of a geometric sequence. So the limit did not exist if R was between less than or equal to -1. There we kind of got an alternating sequence where the terms just got larger and larger. So they alternated between positive and negative and never settled down. The limit of R to the n was 0 if r was between -1 and +1. It was 1, the limit was 1 if r was equal to 1, and the limit was infinity if r was greater than 1. So you can kind of see where these 4 different cases are where they're coming from based on how we worked this limit of r to the n. So we're just going to investigate just to show this case here where r is between -1 and +1. We're going to show that it converges. And I'll leave it for you to look at the other 3 cases here. But really, it comes down to calculating the limit of our sequence of partial sums. And we know the limit of r to the n in this case is 0. And let's just fill that in. So we know the limit of that r to the n term. That's where all the action's happening here is 0 in this case. And so let's just fill that in. So this would be a times 1 minus 0 over 1 minus r, which ends up being a over 1 minus r. All right, so this is for the case so the fact that we get this number here tells us our series is convergent, and this is actually the sum. So I'll leave it for you to kind of work through the details for those other cases. But this limit here of r to the n would be helpful. All right, let's kind of see an example. Example 1. Let's determine whether the following geometric series is convergent or divergent. And if it's convergent, let's find the sum. And we can kind of tell that it's a geometric series because we have this constant number raised to the power n. So it helps when we see this kind of format here where we have a number raised to the power n. Let's just start by writing out our general geometric series, a times r to the n. And then we just kind of match things up. So we can see here our a value kind of matches up with that 5. It's the number in front. There's no n here, just a constant in front, sort of like the a. And then the r value, that's the number that's being raised to the power n. And that's what we're seeing here. R is raised to the power n. In our series here, it's 1/2 raised to the power n. So we have this geometric series, and we can kind of identify just by looking at it what the a value is, what the r value is. And just by looking at the r value, we can say if the series converges or not. So this is convergent since this is a geometric series with r equal to 1/2. And the absolute value of that r value is less than 1. So this is a convergent geometric series. We know it's convergent because the r value is 1/2, and 1/2, the absolute value of 1/2 is less than 1. But we can actually go a little bit further than that. We can actually say what the sum is. So the sum is a divided by 1 minus r. And we've identified a and we've identified r. So a is 5, r is 1/2. So let's just fill in the values. So 5, 1 minus 1/2, we end up with 10. So the sum of this series is 10. Okay. And we could actually say that. We could say this is equal to 10. All right, so, this one, everything was kind of formatted nicely. It is helpful to remember some of our exponent rules. So sometimes we have to do a little bit of work to get it into this form where we have a times r to the n. So let's kind of remember, maybe we'll use b. So if we have addition in the exponent, what happens? Well, it becomes multiplication in between base terms. If we have subtraction, so in the exponent, that becomes division. So we get b to the m divided by b to the n. If we have multiple exponents, so if we have multiplication in the exponent, well, we can really think of that as just having multiple exponents. So b raised to the m times n is the same thing as b raised to the m, and then that whole thing raised to the power n. And then going from there, what else? We have, kind of our distribution or factoring type rules. So if we have a times b raised to the power m, that's the same thing as a raised to the m times b raised to the m. Or for division, if we have a divided by b all raised to the power m, we can think of it as either distributing, or we could think of it as like factoring off. So we can kind of go back and forth here. So sometimes we might have it like this, and we want to break up the exponent, so we can kind of like distribute it almost over multiplication or division. But a lot of times, especially for these geometric series examples, it'll be kind of written out like this, and we kind of want to factor off the exponent. So you can work with these in kind of both directions. So let's try an example where we have to use one like that. So there's a few more here in the lecture notes that I'd like you to try and, try for yourself. But example 2 is really going to kind of cover all of that. So these ones are good practice. So try these for yourself. And I have the solutions worked out in the notes. But try them. Good practice. All right, let's go to example 2. So here we got a bit more going on. We have the series from n equals 0 to infinity of 3 raised to the 2n plus 1 times 6 raised to the 2 minus n. And we kind of have the feel that it's a geometric series, again, because we see constants being raised to the power n. But there's a little bit more going on in the exponents here. And so the idea is we want to try to rewrite these in that general form. So you always want to keep this general format in mind. A times some number raised to the n. So right now we have these kind of two terms with raised to the n in them, but then there's extra stuff up there as well. We just want that exponent n. And we just want a single number being raised to the power n. So somehow we want to split off all this extra stuff and combine them. And that's what we're going to do. And we're going to do this using all of those exponent rules. All right, so let's just start with our series here. And right away we see there's this plus 1 and there's this 2. So we're adding in some extra numbers here. So what we can do is we can just split those off. This plus 1 is just giving us an extra factor of 3. This plus 2 is just giving us 2 extra factors of 6. So let's separate both of those off. So I'm going to take this, and we're just splitting up. We see addition here in the exponent. So let's just factor off an extra copy of 3. And same thing for the 6 to the 2 minus n. We could really think of that as 6 to the 2 times 6 to the negative n. And if we really wanted to go all in, we could use that subtraction rule from before, which would essentially convert this into division. But we'll do that in another step. So you could probably consolidate some of these steps. We're just kind of showing it all here. All right, so now we have the 3 to the 1 is a constant, the 6 squared is a constant, and then we have this 3 raised to the 2n, and we have this 6 raised to the negative n. So let's deal with that 3 to the 2n first. What can we do with that? Well, we can write that as, we have multiplication in the exponent. So we can really think of that as 3 squared raised to the n. So when we have multiplication in the exponents, it's the same thing as like having multiple exponents. All right, so that deals with the 3 to the 2n. Let's group these constant terms, the 3 and the 6 squared. Let's put those all in the beginning here. Those don't have any n's in them, so let's get them all together. And then what about the 6 to the negative n? Well, we know we have a negative exponent, so what is our kind of usual strategy for dealing with negative exponents? We write them as a fraction. So I'd write that as 1 over 6 to the n. Again, you probably could have done that all in one step, but we're just kind of showing everything here. All right, so let's simplify the 3 squared. That's going to give us 9. So we'll have 9 raised to the n. And let's consolidate all of these terms with raised to the power n. Let's put them all together in the same fraction. So I'm going to take this 9 to the n, and I'm going to put it in the numerator here. So I'm going to end up with 9 to the n over 6 to the n. And we have one more exponent property that we can use. And that's essentially factoring off this common exponent. It's the same exponent. We can factor that off. So we have 3 times 6 squared times 9 over 6 raised to the power n. And it took us a few steps to get there. We had to use some exponent rules, but now this is in the correct format. So this is a times r to the n. And you can kind of see 3 times 6 squared, we could have multiplied that out, but that's our a value. And then the r value is this number that's being raised to the power n. And what we have here is our r value is 9 over 6. It's the same thing as 3 over 2, and that's greater than 1. Or equal to 1, I guess we could say. So that r value is too big. So since the absolute value of r, well, let's kind of write it out a little bit more. This is a geometric series and we know it's a geometric series because we just wrote it in that form. This format might not quite look like a geometric series. We see those powers of n, which kind of tell us that it probably is, but we were able to rewrite it so that it actually is in the format with r equal to 3/2, and the absolute value of r is greater than or equal to 1. So this series actually diverges. The r value is just too big. So if we tried adding up all these terms, essentially what would be happening is the sequence of partial sums is just getting bigger and bigger. It goes to infinity. All right, let's try another example. So this was a more complicated geometric series where we had kind of this sigma representation. Let's look at example 3, where we're going to determine whether this geometric series is convergent or divergent. And if it's convergent, we'll find the sum. But here we just have it written out. We have the first few terms written out. All right, so we have to figure out a, we have to figure out r. And we can kind of see that it looks like a geometric series. So why do we think that? Well, if we look at the denominator, what's happening in the denominator? As we go from term to term, we go from this term to this term, we multiply by 3 in the denominator. So we go from this term to this term, we multiply by 3 in the denominator. Same thing's happening in the numerator. So going from these two terms, we multiply by a factor of 2. Then we're multiplying by another factor of 2. Another factor of 2. So, as consecutively, as we go down the line here, we're multiplying progressively by more and more copies of 2 and more copies of 3. So when you see this type of behavior, this is an indication that it could be a geometric series. And how do you actually find it? Well, let's write out what the general form is for a geometric series written out. So the first term is a, then the second term is a plus r, then a plus r squared, a plus r cubed, and so on. And so for a geometric series, we know we need to figure out the a value and the r value. And you can tell just by comparing the first term tells us what a is. So a is equal to the first term. So in this case, 2. Well, how do we find the r value? Well, if we look, the second term is a times r. The first term is a. So we can essentially take the second term, divide it by the first term, and that's going to give us r. So the second term is a times r. The first term is a, so if we divide, the a's are just going to cancel and we're going to be left with r. So let's do that for this work here. So the second term is negative 4/3. We're dividing by our first term, which is 2, and we end up with negative 2/3 as the r value. Now, we should actually go through and kind of confirm this a little bit more. So we have some other terms here. Sometimes you might see it where you have the first few terms written out and maybe the first couple terms don't fit in with the geometric progression, but then after a certain point, that's when the geometric progression kicks in. So, we want to check to make sure that we're actually kind of capturing the correct a value and the correct r value here. So we have some other terms. So our third term here is ar squared. So let's confirm. So we just want to confirm the other terms. All right, so third term. What would be our third term? Well, that's going to be a times r squared based off of this. So let's fill in the values that we calculated, and hopefully they match. So our a value is 2. Our r value is negative 2/3. We square it. And then when we do this, we end up with negative 2/3 is 4/9. Squared is 4/9. And then we have another 2. We get 8/9. And we see that that matches. Matches up with our third term there. Good. Let's just double check the other term as well. So our fourth term. What about our fourth term? Well, this is going to be a times r cubed. Just going up to our general format here. A times r cubed is the fourth one we see. Let's fill in our values. So it'd be 2 times negative 2/3 cubed. And if we cube that out, we get negative 8/27. And then multiplying a 2 in, we get negative 16/27. And that actually does agree as well. That's what we see right here. So we went through and confirmed the other terms. So as long as this pattern continues, which that's what these dots indicate as the pattern continues, the a value and the r value here that we found are correct. So we could write this as if we wanted to rewrite our series, we could write it as the sum from n equals 0 to infinity of 2 times negative 2/3 raised to the power n. And we can actually figure out the sum of this series because the r value here is negative 2/3. So this is a convergent geometric series. Let's state our r value here. R is equal to negative 2/3, and the absolute value of r is less than 1. So we can have convergent geometric series where our r value is negative. And let's actually figure out the sum. So the sum is, the formula is a divided by 1 minus r. We know our a value is 2. We know our r value is negative 2/3. So we end up with this kind of double negative here. And if we do the arithmetic, what do we get? We get 2 over 5/3, which is 6 over 5. So the sum is 6 over 5. And we know that it's a convergent geometric series. Not bad. All right. So this was one where we had the terms kind of written out, and we had to identify, the a value and the r value. And you can use this strategy. We could have done something like this in example 2. So sometimes when you have this kind of this series, this sigma notation version, you can kind of go through this argument like we did, where we play around with the exponents and use all these exponent rules. But sometimes it might be easier to just plug in and actually write out the first few terms of this series, and then actually figure out your a value and your r value like we did here. So that's another kind of strategy for these, is especially for these more complicated ones, like we saw in example 2, maybe just write out the first few terms. First term is our a, second term is a times r, and then you can quickly figure out the r value. So again, you'd want to go back and check it, make sure that everything matches up kind of like what we did. But that's another option here. Instead of going through all this, it's good to be able to do this in general, but there are other ways you might go about this. All right, one more example here, one little application. So these are kind of fun. So we can think of repeated decimals as kind of in some way involving geometric series. So in this example, we're going to write the following decimal as a rational number, and we're going to do that using a convergent geometric series. So, the decimal we're looking at here is 3.9 repeating, or writing that out, it's just 3.999, and it keeps the 9s repeat. And what we're going to do is we're going to use a geometric series here. And really, it's this repeated portion, these repeated decimals, that we can think of as being a geometric series, some kind of representation for a geometric series. So let's think about this decimal. We can really think of this as a series based on all of the decimal places, especially the decimal places that are kind of being repeated. So we can think of this as having a 3 in front. Then that decimal place 0.9, so plus 0.9. Then the next decimal place 0.09. And then the third decimal place after that, so 0.009, and so on. And maybe one more. Just helps to sometimes write out a few terms here. So then we'd have 0.0000009. Make sure I said enough zeros. There we go. And then that keeps going. All right, so you can kind of see the 3 is probably an outlier, but the real kind of geometric progression is going to begin right here. So we can think of this portion as this is where our geometric series is going to kind of kick in. The 3 in front, we can deal with that later. Really, the interesting geometric series portion here is going to be with these repeated 9 decimals. All right, so let's see how we can write this as a geometric series. So we're going to have 3. And then what about this 0.9? Let's write it as a fraction. So we could think of that as 9 over 10. Then what about this one? 0.09. Well, we can think of that as 9 over 100. Then 9 over 1,000. And then 9 over 10,000. And so on. And so what we're seeing here is the 9s are staying the same. It's just we're increasing the denominator by a factor of 10 each time. And to really drive this point home, let's write these as powers of 10. So 10 would just be 10 to the 1. 100 we could write as 10 squared. 1,000 we could write as 10 cubed. 10,000 we could write as 10 to the 4, and so on. And again, we're thinking of these fractions here. This is our kind of our geometric series portion. The 3 is kind of something, it's behaving differently. We can kind of push that off to the side for now and really worry about, does the actual, most of the terms we're adding together here, are they convergent or not? Are they a convergent geometric series? So what we're thinking of is, this is our first term, a. This is a plus a times r squared, a times r cubed, and so on. And we want to find, we kind of see each time we go through, we're increasing by a factor of 10 in the denominator. So we really think this is a geometric series. And by comparing, we can see that the a value is 9 over 10. And the r value we can find by just taking our second term, dividing it by our first term. Just like we did in the last example. So in this case, r is going to be 9 over 10 squared divided by 9 over 10, which ends up just being 1 over 10. And that's what we were seeing, really. Each time we were going through, we were increasing by a factor of 10 in the denominator. Well, this r value is less than or it's the absolute value of this r value is less than 1, so we know this is a convergent geometric series. So we know it's convergent since the r value we found is 1 over 10, and the absolute value of that r value is less than 1. So we know it's a convergent geometric series. So we can actually figure out what the actual sum is for all of these values here. So in this case, the sum is a divided by 1 minus r. So let's actually figure out what the sum is there. Well, our a value is 9 over 10, and then our r value is 1 over 10, and let me do this down below. So we actually know the sum here. Our a value was 9 over 10. Our r value was 1 over 10. And if we do the subtraction here, we end up with 3 plus 9 over 10 divided by 9 over 10, which is just 3 plus 1, which is 4. So what we're able to show is that this decimal 3.9 repeating, we are able to express those repeated 9s as a geometric series, find the sum of that geometric series, saw that the sum is actually equal to 1, and that's the one that we're seeing right here. And then this 3 that really didn't fit in with the pattern, we kind of kept that along. And then we just added the sum of our geometric series with that 3. So 3 plus 1 gave us 4. So to write this decimal as a rational number, well, this is an integer. So, what is a rational number? It's p divided by q, where these are integers. So, we could write it as 4. If we wanted to really express it explicitly, we could write that as 4 divided by 1, an integer divided by an integer. So we were able to write this repeated decimal, 3.9 repeating, as this rational number 4, which that's pretty cool that we were able to show something that kind of doesn't look like it should be equal to 4, but it actually is. So you can do this with all sorts of different series where you have these 3.9 or 2.9 repeating or 5.9 repeating. This 0.9 repeating is actually another decimal representation for the number 1. So it's just an interesting fact here. Based on geometric series, we were able to show that 0.99 repeating is actually another representation, another decimal representation for the number 1. And that was the sum of that series. So it's always surprising to see that, but it is. All right, so that's just a fun little application of geometric series. All right, so next time, so geometric series is one of our special forms. We're going to see another special type of geometric series, or another special type of series that we know quite a bit about, called p-series. And really, these two series, the geometric series that we're seeing in this lesson, and then the p-series that we're going to see next time, really those are our two sort of building block series that we're going to be talking about quite a bit. So we'll see the p-series next time. So we'll see you then. Bye-bye.